All right. So next talk is going to be given by Mahajan, and she's going to be telling us about charges and about harmonic current switching in DC.
So good afternoon, everyone. Yes, I'm thankful. I can-
Check.
hold. So good afternoon, everyone. I'm really thankful to the audience for this. And today I'm going to talk about is I'm sorry. So yeah. So today I'm going to talk about this morning current switching layer by using the okay. Is it fine? Mm. Okay. So this talk is done in the PhD. Let's look at the content. So first I'll give a brief about then I'll introduce the concept of transcripts. Then how to place how to place phase transition into the phase. Then we explore the electrically driven transitions in a layered hedges. Then I'll conclude. Alright. So first, the transition let me write out for me. Layer one metal sheet is sandwich between chalcopyrene sheets thereby forming a PMD monolayer, and each layer is connected by a weak cannibal forces. So out of all these TMD materials, two-thirds of these TMDs are layered, especially from group 4 to group 7, and these host a wide variety of properties, including the insulating semiconductor immunity, semiconductor WP, and metallic NBS. So the inner behavior of these materials usually arises from the van der Waals forces in each one. Out of all these materials, the half-filled D-band dipole, especially the TS2, exhibits unique charge. What are these charge density waves? These correspond to modulation of density with respect to the atomic. So the impart unique features in the four-dimensional solids. Let us understand the concept of charge density waves by considering the one-dimensional metal with a half-filled band without any electron interactions. Here, if you see the state becomes energy is EF, and in the following wave EF, the states are filled and the states are empty. Now, if we consider the electron form interactions, repeats, it will result in the opening of the gap at the point. Since the states EF were filled, so the opening of the gap EF reduce the total electronic energy of the system. So, the decrease into the increase in the elasticity. CW is potent is the preferred branch. However, at a high being out, to the underlying lattice, CW C to P C to N. All these C to P
The low temperature C phase is kind of represented here by a triangular superlattice, which is formed by these David star structures. So these David star structures are formed by the inward displacement of 12 tantalum atoms at the location B and C towards the 13th tantalum atom as the center of the star. So these atomic displacement or the shrinkages in the AB and BC bond length results in the swelling at the center of the star. So this bond length shrinkages actually results in the disintegration of band structure of TeS2 into various submanifolds, wherein the 12 tantalum atoms which were arranged at the corners of the stars contribute to the submanifolds in the valence band, whereas the 13th tantalum atom, which was located at the center of the star, contributes to the electron in the conduction band. Now the on-site Coulomb repulsion between the electrons in a very small band at the Fermi level further localize the electron, and it will result in a Mott-Hubbard transition. So this is the reason why we have a very high resistivity of TeS2 at low temperature. All right. So the CDW phase transition, interestingly, can also be invoked by current-induced Joule heating. So the NCIC phase transition that happens at around 353 Kelvin can be obtained or induced at room temperature by simply applying a high bias across it. So we apply a high bias across a TES2 device, and what we found that we see a abrupt current increment, which is around a factor of around 1.5, and which is similar to that of the NCIC phase transition. So this is further confirmed by the simulated temperature profile across the TES2 channel, which we did using FEM, and what we found that after the bias is increased from 1.8 to 2, the temperature in the middle of the channel is sufficient to induce the NCIC phase transition, which is above the 350 Kelvin. All right. So however, even though it is very interesting that we can induce these transition at electrically, there's a bottleneck to it. The switching ratio is very small, which is around 1.5, and also we cannot gate control it since it's a very highly conducting material. So what we propose here, we propose a new architecture, new device where we could achieve a high current switching in this triple layered heterostructure, where MOS2 is the bottom, followed by a dry transfer of TASE2 and a TAS2. So the idea is to, whenever the abrupt change in the TAS2 current happens, that will result in the abrupt change in the temperature, junction temperature, which will induce the kind of thermionic carriers into the MOS2, and which eventually modulate the MOS2 current. All right, so this is the 3D schematics of the device. To do that, first we do that, we try to achieve NCIC phase transition in this TES2 and SE2 branch. So we apply a high bias and we could achieve it, and the factor was somewhere around 1.5. So which means that TES2 carries ample amount of current to derive the NCIC phase transition of TAS2. All right. So in this, the first thing is that why we use TASE2, there are multiple reasons. One which I just stated, that we need ample amount of like current to drive the NCIC phase transition in TAS2. Secondly, the low thermal conductivity of TASE2 in comparison to gold further helps in actually increasing the local temperature of the channel, which will further help in the thermionic transport. Also, this TASE2 acts as a buffer layer between TAS2 and MOS2, which will prevent the Schottky barrier modulation at TAS2 MOS2 interface, which usually happens with the simultaneously with the phase transition. So it kind of acts as a buffer so that we don't see the effect of Schottky barrier modulation due to the phase transitions of TAS2. So this is the equivalent circuit of the 4-probe device, where R1 R1 represents the resistance of TESE2, R2 represents the resistance of TES2, and MOS2 R3 represents the resistance of MOS2 branch. So there is an external 4 terminal, which is the universal backgate. So what the idea is to apply a high bias across TESE2 and TES2 terminal, and while simultaneously monitor the MOS2 current. Even though we were looking for increment, but what we found that when we apply a bias across TESE2, enough high bias which can induce the which could actually cross the threshold for the TES2 NCIC phase transition, it will abruptly increase the current in the TES2 branch and simultaneously reduce the current in the MOS2 branch, which will contribute to NDR in the our current characteristics. So this is for both TES2 and MOS2 injection, and we see NDR in both the sides, and we extracted the PVCR. So we could achieve a PVCR of about 1.12 modulated through the gate voltage because of the modulation of MOS2 resistance by the backgate voltage. And this is the PVCR that we could obtain at room temperature. So to a simplistic way to further improve this PVCR is to induce the low temperature phase transitions of TAS2. So we perform all these measurements at 150 Kelvin. So the current ratio increased to 1.7, and we could increase the PVCR at 150 Kelvin to about 1.27, which was better than the room temperature values. Now, interestingly, if we change the biasing conditions and we apply the bias as TAS2 instead of TASE2, we saw a current increment. So here, the only difference is that when we apply high bias, the TAS2 current changes abruptly, and it will simultaneously increase the current in the MOS2 because now the total current is going through R2 instead of R1. So we got this current increment factor as high as 1.5 at room temperature. To further increase this, we again perform low temperature measurements where we try to invoke the low temperature C to T transition of TAS2 through the external electric field, and we could achieve a current increment factor of around 4 at 150 Kelvin. So this current increment factor cannot be solely achieved by the TES2 phase transition, because at 150 Kelvin, it was limited to 1.7. So there's another mechanism that is happening, and that could probably explain why we see such a high current increment factor. So to understand that, let's see a simplistic mechanism, schematics to understand the mechanism of thermionic injection in this case. So this is the situation before the transition, and this is the situation after the transitions. So what happened that when the TES2 transition happens, there is a suddenly increase in the current, but at the same time, there will be a local increase in the temperature because of the current induced Joule heating, which will further ignite these, transfer the kinetic energy to the carriers, and they can easily cross the thermionic barrier at the TESC to MOS2 interface. To further explore this, what we did that we designed a new device where we have reduced the MOS2 channel to, we designed a new device where we have a very narrow MOS2 channel and the junction overlap area is reduced. So what we are essentially doing that we are trying to pass the very high hot electrons through a very small region, which further helps in increasing the local temperature and which kind of acts as a local heater. So here we could able to achieve 2 times current enhancement at room temperature, and then at low temperature we could see a current enhancement by a factor of 3, almost 3 orders of magnitude. So this is the current enhancement factor variation as a function of temperature. So we see that as we keep on lowering the temperature, base temperature, the current enhancement factor almost reaches, changes to a fact almost by 3 orders of magnitude. This is because we are trying to invoke the low temperature metastable states or C to T states of TAS2. So here if you see, there is a very strong non-monotonic behavior in the current increment factor as a function of Vg. This can be explained by these band diagrams. So what we so for each region noted here, especially for this is for Vt greater than 0, that is MOS2 injection, and this green line shows for the Vt less than 0, that is like for TS2 injection. So first I'll talk about MOS2 injection here, and for Vg very less than 0, which is around somewhere here, so the electrons can easily transfer through, they don't see any barrier and they can easily jump into TAC2. For Vg almost equals to 0, which is region B, they see a thermionic barrier and we see a very high sensitivity towards the current, and there is a high current jump as well. So what we do try to simulate the temperature at this point, and what we found that for a base temperature of 77 Kelvin, we could actually achieve at a certain very high bias, the temperature of the channel could reach as high as 230 Kelvin. So further, we try to simulate certain current ratios for a variable barrier height at the TAC to MOS2 interface. And what we found that from 120 to 240 Kelvin, with respect, we find these current ratios for these temperatures with respect to the 77 Kelvin base temperature, and we found that we can have the current ratios as high as 10 raised to power 4, which kind of justifies the high current ratio at this region. Next, in region C, for Vg much greater than 0, there is a band bending increases and the electrons can simply tunnel through. So now the transport is generally dominated by tunneling, and we have a low current jump because it is not further controlled by the thermionic barrier. Right. For TAS2 injection, similarly, we see that for Vg much less than 0, there is a barrier and then there is a high current jump because then it is sensitive to the local temperature. And similarly, for Vg greater than 0, there is a tunneling happening and your current increment factor kind of reduces. So to conclude, we show here today the current switching ratio up to 964, up to a factor of 964 driven by a CDW phase transition, and which is almost 190 times higher than the existing reports. Also, we show a very highly reconfigurable device that can easily toggle between the NDR as well as the current increment by simply changing the biasing conditions. Additionally, this gate tunability, which comes because of the MOS2 modulation of MOS2 resistance with the backgate voltage, this can be useful for various sensing applications such as the current and temperature sensors. And further, it can find potential application in various oscillators, switching circuits, and neuromorphic chips. So I want to thank my PhD advisor at IISc Bangalore, Kaushik Majumdar, and my lab mates at QEL. Also, I want to thank all the funding agencies, and thank you.
We have time for some questions.
So it's microscopic. I mean, like at structure level, if I see, then there is a superlattice formation, the triangular superlattice. Then there is, which is resulting from David star formation. So when you try to apply a high field, those stars break up, and then your kind of resistance is going down. So you have a high current jump. So I hope that answers. Sorry. No, it depends upon how much you can drive the local temperature. So you can break, like if I'm at say room temperature or which regime you are operating. Like if I'm at a base temperature of 77 Kelvin, and if I'm reaching around by just through external bias, I'm trying to reach the local temperature by say by simulated results, which I've shown that 230 Kelvin, which means that it have already crossed the C to T transition. So it kind of breaks the whole system. So it depends upon which temperature you are reaching, purely depends upon the bias or field you are applying. Yes. No, I we did the stability measurements. Even like for certain devices, even after 1 year of usage, they show this kind of data. I mean, just no any fancy kind of storage, just kept in a desiccator. So it did replicate the same current after 1 year also.
Speaker once again.